So let's record this creature. So one of the things we want to do is let's recall Newton's method. So we're not going to do all the specifics. We're going to do the baby-fied version we did in Calculus 1. So Calculus 1, Newton's method, allows us to approximate. So I'll put the word solving in quotation marks because we're not finding an exact answer. But we are solving an equation of the form some expression in terms of x's equals 0. So how it works is the following. It works, and I don't want to go through the geometric argument, but it works by looking at, well, maybe I can do it real quick. Here's how it works, just for a brief overview. And again, this is not the physical, or this is not the technical details. But imagine we have some curve that crosses the x-axis, like down here. So imagine it. This is some function which I'll denote y equals f of x. So it's some graph. And what we notice is it has a solution. So let's call this solution, let's say it happens at C. Now the question is, we want to know what C is. We know that it crosses, and how do we know when things cross? Well, we have other tools like the intermediate value theorem, or we can use, remember in calculus we said if it's increasing and it has certain properties, then it has to cross, because if you keep going up, then you have to cross, stuff like that. So there's ways we know that a solution exists, and the question is how do we approximate it? And so the idea behind Newton method is you take some guess. So I'll use a different color, let's say green. So Newton says, let's make a guess on what the root is, the solution of the equation, and let's call it x1. So what we do then is we look at the tangent line of y equals f of x. So if I go get my line here, if I look at the tangent line at that point, what I notice is that tangent line crosses the x-axis at some place between x1 and c1, if I make a good enough guess. So we'll call this intersection point, this is x of 2. And then if I play the same game here, I can find the tangent line here, and then I notice that crosses, that was bad. What we notice is that tangent line will cross, close to C. So what you're doing is, by playing this game, you're generating a list of numbers. You're getting your list of numbers, and we'll just denote them as a sequence. So we're finding x of 1, x of 2, x of 3, etc., with the idea that the limit as n goes to infinity, we're creating a sequence where the idea is the limit as n goes to infinity of this sequence equals C. So before we do anything else, it's imperative that you understand this. We're generating a list of numbers, and we're generating them in a very sort of algorithmic way. We're going to make a guess at first and say this number looks close to C. And then we're going to generate more values in this sequence by repeating the same process over and over again. So what you'll notice is what is the point x of 2? Well, x of 2 is the point where the tangent line, so let's just look at this for a second. If you look at this line right here, this green line is y equals mx plus b, but we don't want to think of it as y equals mx plus b. We know what it is from calculus. What is this line? Well, this line is y equals, and then it's the derivative evaluated at x of 1. That's the slope. And then it's x minus x of 1. And then, of course, it's plus f evaluated at x of 1. That is the point slope equation of a line. So that's what this green line is. And so what we can do is if we set y equal to 0, if you take this thing right here and you set y equal to 0 and solve for x, you get the following. So I'm going to go to the next page and let me remind you what this equation was. So what we have is we have y equals f prime of x sub 1 times x minus x sub 1 plus f evaluated at x sub 1. So that's what we have for that first line, that first tangent line. And so set y equal to 0 and solve for x. So if you do that, set y equal to 0, so you take the f of x sub 1 to the other side, you have minus f evaluated at x sub 1 equals this. So I'm going to do a couple steps of algebra at the same time. And then when I take this to the other side, it becomes f prime x sub 1. I'll put the x sub 1 out front, and then it's, of course, minus f evaluated at x sub 1. Oh, this is times. And then I'm going to divide both sides by the slope, f prime evaluated at x sub 1. And when I do that, I get x sub 1 minus f evaluated at x sub 1 over f prime of x sub 1 equals x. So this right here is the x-intercept of the tangent line. So then once we give it a name, so since we already called the first guess x sub 1, what we'll do is we call it x sub 2. So this is the general idea behind Newton's method. And we can just repeat this game over and over and over again. And what we find under the correct situation, as long as we make our guess correctly and the derivatives have certain properties, things are nice, which we're not going to worry about the bad things in this class. But if things are nice, then this sequence that we generate will converge to the actual root. And so what we do is we have this pattern. If we do it in general, we can denote, so in general, you have the nth plus 1 approximation is equal to the previous approximation minus f evaluated at the previous approximation divided by f prime at the previous approximation. So this is the optimal thing right here. This guy is really what we're after. This is the key to solving these things. Now, you can do this by hand, but it's tedious, right? So why not let the computer do it for us? So that's what we want to do. So before I go to the computer, do you guys have a question about this? Comments, concerns? So anytime you can define a sequence this way, we call this a recursive sequence, because look what happens. The new term in the sequence, the second term is defined based off the first term. And then the third term is based off the second. And then the fourth is based off the third. And in general, the 100th term depends on what is the 99th. Or the nth plus 1 term depends on the guy who comes before n plus 1, which is n. Anytime you have a recursive sequence like this, you can do them by hand, but it's very tedious. However, a computer can quickly do this, very, very, very quickly. So let's look at a very simple example. I forget what I gave you guys on the homework. Let me pull it up. I don't want to steal the fun from you. But yeah, I guess we'll give you the first one, x squared minus 2. That'll be fun. We'll do that. So let's do this by hand, and then we'll see that it's tedious, and then we'll go to the computer. So this guy has 2 roots, or 2 solutions is a way of saying it. What would you call them? You usually would write them as x equals plus or minus the square root of 2, but let's suppose we would like to know what the actual value of the square root of 2 is, not just some symbol 2 inside a weird symbol, but what is the value of this number? I mean, our intuition tells us it's between 1 and 2, but what is its precise value? How precise can we get? So here's how we can do it. If we wanted to use Newton's method, we can say set f of x equal to x squared minus 2. And of course, that means f prime of x is 2x. And so let's guess that the positive, so we know there's 2 solutions. So let's just look for the positive one for now. So let's guess that x sub 1 is equal to 3/2. Why am I guessing 3/2? Well, that's because it's halfway between 1 and 2. That's the only reason I'm guessing it. You could guess something else, but I'm going to guess 3/2. So what's x sub 2 then? Well, x sub 2 is 3/2 minus f evaluated at 3/2 divided by f prime evaluated at 3/2. And so I would go to a calculator to do this, maybe Desmos if I wanted. So, or your handheld calculator, it's up to you. So let's say, I'm just gonna go to Desmos and do it for now. And because I'm very confident you guys can do this on your own. So let me do this real quick. So if I go and plug this stuff into my calculator, if I plug 3/2 in here, what I get is this equals 1.41667. And so then if I want, I can go compute the next guy using this creature. And of course, you could see right away this would not be something you wanted to do by hand. But if you were brave enough to, or if you were, I don't know, if you wanted to drive yourself crazy, I guess you could do this by hand. And so if I plug, if I compute this number, I get, I put the number in wrong. It's 1.4. So if I plug this in, it's 1.41667. So what I end up getting is 1.4142. And I guess I'll go one more decimal, 0.5. And so then I can do better, because then I can now put this guy in and get the next approximation. And what I notice is I'm starting to get the same number as my output. My x of 4. If I go and do this again, I'll just make a chart here. I don't want to go to the next page because then you're going to miss the glory. So if we look at what's happening, what is your x sub 1 was 3/2. X sub 2, we get 1.41667. X sub 3, you get 1.41421. And then when I get my x sub 4, you know, I get 1.41421. So I match, even though if I go further down in my decimal point, they don't match. But what I'm starting to see is that I'm getting convergence here. At least I think it is. And it turns out theoretically we will get convergence. And so now what we know that the square root of 2 is approximately 1.4142. Now, if you went to your calculator and did that, if you just went and typed the square root of 2 into a calculator, you're going to see that decimal, right? So does this make sense? At least doing it by hand. I don't know if it makes sense or not. And then we're going to show you how to do it by computer, though, because the computer will do it all in an instant as long as you program it nice. So one way to think about what you see here is this column is this keeps going and going and going. What's happening here is this number is converging to the exact value of the square root of 2. And so you can get it to any degree of accuracy you want. If you want 3,000 decimal points of accuracy, you can do it. And actually, you could take classes where you study these convergences and how this works. But now's not the time for that. Okay, so how do we get the computer to do this? So what I'm going to do is I'm gonna pull up my screen here. So let me see how I can do. Do you guys have any questions before I pull up this stuff? Any questions? All right, so I'm gonna. Are you guys seeing my desktop right now? What do you guys see?
Yeah.
All right, are you seeing Octave loading up? Hopefully. Let me see if it loads up. So let me know if you guys see Octave. And then the first thing I always do when I open Octave is I make sure, are we seeing Octave? We good?
Yes.
Yeah, okay, good. First thing I do is I go to this window on the left and I make sure I open whatever folder that I'm going to have my files in. So for me, I have all this saved in my Octave. So, but what maybe I'll do is to make life easier on you guys is I'll go back up one and I'll go to my folder for this class. So maybe I'll go to, where's it at? So my courses at La Roche, and then I have summer 2020, and then I'm going to make a folder in our class. Our class is, no, this is the wrong thing. What did I hit? Spring. I want summer 2020. And so let's say I create a new folder in here, or maybe, okay, I'll just throw it in here for now. So what I'm going to do is I'm going to go to my editor and I'm going to ask the computer to do this for me. So I'm going to just remove these from my editor. And the first thing I'm going to do is I'm going to give this a name. So let's say we're going to have a new guy. And so let's give it a name. So since we're using it for this class, let's call it, I'm going to just call it Newton. Summer 2020. So notice how I named this file. Notice I'm using these underscores because you can't put spaces in file names. So I'm just going to name it this, Newton Summer 2020. And the first thing I'm going to do is I'm going to go and save it. So I go to File, and then I'm going to Save As. And look where it's at. I'm making sure it's in this window that's over here. So I'm going to save it here. And so I got to make sure I could have copied and pasted, but I'll just type it in manually. All right. And so what we're going to say is the purpose of this file is to use Newton's method to approximate equation or solutions. Let's just speak real quick. Roots. We want to approximate roots. Now, don't forget, this needs to be commented out. Okay, so how are we going to do this now? Well, in order to use Newton's method, we have to set the problem up right. So the first thing is we need to know what equation we're trying to solve. So let's say approximate roots, and then I'll go to the next line of f of x equals 0. Right, that's what we're trying to solve. And so that means we need to do a couple things. We need to tell it what f is, and there's a lot of ways you can do this. And I'm going to show you how did we do it last class. We used this thing called inline. So let's remember how to do that. Does anybody have a question, by the way? Comments? Okay, so here's how we do it. Let's tell it what f is. So the way we do this is we say, okay, f equals, and what you have to do is you say inline, and then you put a parenthesis, and now we have to tell it what the rule of the function is. What is the rule of our function? Well, remember, we're going to put this little quote thing here, like apostrophe. And then what is our rule? Our rule is you take the input, which we'll call x, you square it, and then you subtract 2. And then that is the rule, and now we have to tell it what the variable is, and the variable is x. So we will do this. Now, before we do anything, let's make sure this thing works. Right? One of the things I would encourage you to do when you're first learning it is every time you put a line of code in, make sure it does what you want it to do. You don't want to just write 10 lines of code and then when it doesn't work, have to figure out why it didn't work. So let's see, does this thing work? So how do I test it? Well, let's plug a number in. Let's say, okay, I want to plug 10 in. And I should get 98 if I coded this thing right. So what I'm going to do is I'm going to run it. Remember, I can hit this gear. This saves and runs it. And then if I want to see what happened, I go to the command window and it says answer 98. So I feel good because it did my problem correctly. Right? So I plug f of 10 in, and that's what it does. So I feel good about that. Does anybody have a question? So now it knows what f is. Now, this is not a symbolic package, so I also have to tell it what the derivative is. So maybe I'll call this other function fp for f prime, and that is inline. And what's the derivative? The derivative is 2 times x, and of course, the variable once again is x. And so, for example, let's make sure this works. Let's type fp of 3. So when I run this, it should spit out the number 6 because 2 times 3 is 6. So if I go to my command window, great, it says 6. So I'm excited. Are we following? Does anybody have a question? Am I going too fast? I don't know. I hope not. Okay. So now what we want to do is we want to compute this we want to compute these sequences. So let's say f, what are we doing here? Let's just remind you, we are defining the function f of x. And then the next line, we are defining the derivative.
我把药放出来了。
Okay, so now that we have the derivatives, what we need to do is we need to now do Newton's method. So what was the next thing we did? If I go briefly, if I leave this share and I go back to the whiteboard, if we go here, what did we do? First, we defined the function and then the derivative, and then we made our initial guess, and then we computed each successive approximation. So I'm going to do the same thing, only I'm going to have the computer do all the work for me, make it do all the computations, save my brain. So if I go back to my, are you guys seeing Octave again, hopefully?
Yes.
So if I go back here, let's make our initial guess. So before I do that, it's nice to give, what I'd like to do is I would like to give Octave a place to store these values, as it were. Like, where is it going to put them? Is it going to put them in, it seems weird, but where is it going to store these values? So one way to help do this is I can say, I'm going to set X. And it's going, well, okay, I don't want to get too, let me come back to that actually. So we want to compute the value. So here's what we're going to do. What we're going to do is we are going to set our initial guess. So what was our initial guess? Our initial guess is we called it X1. So we'll say X1. And what do we call it? We called it we guessed 3/2. So I'll just write 3/2 in there. And now I don't want the computer to spit it out. So I'm just going to put a semicolon here. Remember, that just doesn't spit anything out. And now what we're going to do is we're going to compute the other values. So what were the other values? Well, these were X sub 2, X sub 3, etc. And the thing about these guys is we can't use subscripts, and so what we'll do is we'll compute them very quickly. So what we'll tell the computer to do is do it for us. And the way you can get a computer to do the same thing over and over again real quickly is, one way is you can do what's called a for loop. So you started off by saying for, and now we need some sort of indice. So we'll use k. So we'll say for k equals 2 to, say, 10 for now. We're going to compute. Well, okay, let me be careful. Let me go to 1 here. So I'm going to do this 10 times. So what's the next guy? The next guy is, and this is almost identical to our formula. You can write k, which is our indice, plus 1, is equal to the previous guy, xk, plus f evaluated at xk. So this is going to look funny because of all the parentheses. And then you divide fp evaluated at xk. And then you type end. And what that does is that's going to calculate x2, x3, all the way up through x10. So if you have a question or comment, please yell at me. Now I got to fix these parentheses. I got some stuff that's off. That should be x of k. So it looks kind of funky because you have lots of parentheses, but it is in fact the way you can do it. So we're not using subscripts. So when, you know, the computer doesn't quite understand subscripts. So what we do is we use parentheses instead. And there's our formula. This formula right here is exactly the Newton iteration.
Wait, what does this for loop mean?
That just means we're going to do it. It's going to do it how many times I want it to do it. So instead of me doing it one at a time, it does them all at once.
But that's what like k1 to 10.
Yeah, so the k says first it says, it's a good question actually, because this is probably not obvious if you've never seen it before. So what it's going to do is it's going to start with k equal to 1. So when k is 1, what do you see? You're going to see what's 1 plus 1. So when k is 1, it's going to say x of 2 is equal to x of 1 plus f evaluated at x of 1 divided by the derivative at x of
1. I see.
And then it's going to do that, and then it's going to store it. And then it's going to take the third one, then the fourth one, and the fifth one. And it's going to stop when k is 10, it'll stop. So the last guy we're going to get is x of 11.
Oh, okay. I see.
Does that make sense?
Yep.
So, and now it automatically stores them in a vector. So what we're going to do is we're going to ask it to write this vector and list it. So we can write it in a column. If I put x, so it knows what x is. X is a vector, and it's going to have 11 elements. x1, 2, 3, all the way up to x11. Now, if I change this number here, Abdullah, if I put this to 5, then it's only going to go up to x sub 6. And if I put 25, it would compute the first 26 of them. Does that make sense?
Yep. Yeah.
Yep. So, so this is a built-in function. This for loop is built in, so it does the computation rapidly. And so what's going to happen now, let's just say I put x3 down. So I'm just going to compute the first 4. 1, 2, 3, 4. That's what we did by hand, right? So we should expect the same numbers that we got before. And so let's look at what happens when I run this. When I run this, I get a list of numbers, and look what these numbers are. And then you say, well, that doesn't look correct. What did we do wrong? Does this look like the list we had for ourselves? No, it doesn't. So we got to figure out where our mistake is. The first number is correct, but after that, things are going haywire. And the question is why? Well, the obvious thing is I typed the formula in wrong. It's not plus, it's minus. So now if I go and run it again, I'm going to get a column. And look, is this not exactly what we got when we did it by hand? So let me see if I can share that. If I go back to my whiteboard, that's exactly what we got when we did it by hand. Right over here. So now we're confident that our code is working properly. And so now we can modify all this to make it do more sophisticated things. So if I go back to this, instead of just doing the first 4 of them, maybe I'll put 10 here. And then if I run it, you'll notice that this thing, it converges very fast to what we expect because the calculator gives us the real answer. But by the way, I can make a change here. I can come up to the top and I can tell it that I want to use more points in my decimal expansion. So I think I showed you this last week. If I type format long, watch what happens. So that tells the computer now to not just use the first 3 or 4 decimal places. It tells us to use more. So if I run this again, now you'll see it does converge really rapidly. I mean, look how many we have in agreement. We have all the way down to what? 1, 2, 3, 4, 5, 6, 7. We're, you know, almost 12 decimal places of accuracy. So that's pretty good. Does anybody have any questions about this?
I'm getting like a different answer. I'm getting just like numbers from -10 to 10 for some reason.
Okay, so yeah, so you're doing something wrong. I wonder what it is. Are you copying my stuff verbatim?
Yeah, I mean, I see that it's all the same. It's not different.
I wonder why. Now it could be that were you playing around with Octave earlier? Does it maybe have F stored incorrectly? Do you have FPs? So what I'm saying is if you were calling something F earlier, so what you could do is at the top, you can hit clear. And if you do clear all, that will erase any things that are already stored. So that could be an issue. I would have to look at your code before I realize what it was, but that could be one issue.
Oh, okay, it's working now because I had like other things open as well, other graph.
Yeah, so what happens is if you used F earlier, it's gonna be confused. It doesn't know what F is. If you defined F to be another function, then you're gonna be in trouble.
Okay.
Yeah. But now you can do the same thing. If you look at the homework, here's a cool look at problem C. So let's just do C real quick. I think this is fun. So all you have to do to finish the homework is you just have to change F and FP. That's it. So what if I did problem C? Well, let me change this. This is going to be, now this is log of x minus 1. And then, of course, the derivative of that is 1 divided by x. And so even if I use the same guess, here's what's going to happen. Look at that. Does that number look familiar? Notice what value of the log spits out 1. Now, if you think about it, you'll remember that the natural log of E is 1. So the solution to equation C should be E, and that's exactly what we're getting. Look how quickly that converges to E, 2.718, blah, blah, blah.
Wait, so like the natural log and log are practically the same thing?
No, they're not. Okay, so that's a great question too. So these older, you know, software is, look, and if you're using, almost all software uses LOG for natural logarithm. And if you wanted like a log base 2 or 10, you have to write it in differently. Does that make sense? So yeah, it's just a weird, I don't know the exact reason why they don't use ln. It might work. I don't know. Let's see. What is ln of 3? I don't know if it'll work. See, ln is undefined for whatever reason. I'm not sure why. I'm sure if you Google it, you'll find out why. I'm going to look it up right now because it's going to make me curious. Why doesn't software use ln? Yeah, there we go. Let's see. So that's the first hit. Why does MATLAB use log instead of ln? Has something to do with earlier languages. See, it's just habit. It's like, here's a good question that maybe you guys have never thought about. You've probably heard of binary before, right? Zeros and ones, and you might know that that's how computers communicate, all in zeros and ones. But that is only historical that we use zeros and ones, because it comes back to the earliest computers where electricity, you had different currents. And so in order to not confuse keystrokes, we used 0 and 1, just 2 options. But nowadays you could probably use 10, 8. You don't have to use base 2. I don't know if that makes any sense to you guys, but it's something that, you know, sometimes we do things years ago and we just stick with them even though they don't make much sense. Does that make sense? So yeah, you'll learn these things as we go, but this is, now look, this is very crude code. I mean, you could do much more sophisticated than this. You can make it print tables and charts if you wanted. And I would encourage you to try to learn all that. But if what I really like you to get is get to this stuff. That's the most important thing. Does that make sense?
Yep.
Very good. Anyhow, do you think you can do these now on your own? I mean, look, I can actually post this if you want, but it seems to me like you're already doing it, so that's good. And by the way, if either one of you wants to meet outside of class to do this, we can sit down and do this together if we wanted to. It's up to you guys. I'd be happy to do that, you know, work through these codes. And another thing I'll say, if you look at the next problem with the integration, it's very much the same idea. Doing Riemann subs by hand is really tedious, but a computer will do them in a second. By the way, here's something else that's cool you can do. If you, at the top, if you type tick, and then at the bottom, you type talk, what that does is that sends a timer. And when you run your code, it'll tell you exactly how many seconds it takes for your code to run. Because there's times, if you get real sophisticated, I'll give you an idea. When I was working on my dissertation, the simulation I was running, it took about 40 hours for it to run, almost 2 days. So I'd have to hit enter on my computer, and I'd have to wait almost 2 days for the simulation to end. And so it was nice to have these timers that help you figure out how long it might be. Anyhow, but look, the best way to learn this is to take basic things like this and then try to make them prettier and nicer. And you're only going to do that by spending time on it, unfortunately. That makes sense?
Yeah, so for question 3, like we're just writing the Riemann sum
Yeah,
equation.
so here, let me get you started. Here's how I would think. I mean, the code I gave you works too, but what I would tell you to do is just do it like you're going to do it by hand. So, give you an example. You can call it, let's give it a name. Let's just call it Riemann Summer 2020. .m. And so here's what we're going to do. We got to give it a function we want to integrate, correct? So let's say f equals inline. And then what are we going to do? Let's say the first one is x squared. So we got to put our thing here, x. Don't forget, you should always be safe and put the period in front of multiplication and division in case you ever want to. It's just play it safe that way. That's the best way for me to tell you. All right, so that's my function f. Now I've used f in another file, so I just to be safe, I'm going to put clear at the top, clear all, so it doesn't know what f is anymore. And then I'll even put format long. And so here's the function we want to integrate. And then we can do things like let's set bounds. So let's set our bounds. And in general, what are our bounds? We call them a. So that here in this problem, a is 0. And then b equals 1. So if you go back to what you did, this is what, and then how do you set what you want to do? Well, how many rectangles do we want? So we should also say that. How many rectangles? Let's say we want to use, let's start with something simple. Let's say we'll call n the number of rectangles. Let's say 4. So if you go back to your definition of the integral in the Riemann sums, the first thing you did is you said, okay, let's get our dx. So what's your dx? Your dx is always equal to b minus a divided by n. So these were, you know, if you want to think of this in a geometric sense, these are the widths of each rectangle. And so then once you did that, then you needed to compute, how did you compute your x's, your points in your partition? Well, you had to do that by hand, but there's a simple formula. So what are they? So what is x sub 1 and what is x sub 2? So here you go. It's quite easy to do. You can write a for loop, and you could say, let's use k again. K equals 1 to, where are we going? Well, we're going to go to n, right? So for k equals, actually it's 1 to n plus 1. So what are these guys? Well, the first one is, so the first one, x sub 1, what is x sub 1? X sub 1 is a plus delta x. So in general, what was the formula? The formula was x sub k is equal to a plus k. So you have to be careful. You might have to review some of this. Times, it's k minus 1 delta x. So what this does is this computes your x sub 1, your x sub 2, all the way up to, you know, up to how many you're going to have. So if we're going to have 4 rectangles, how many points do I need? I'm going to need 5 points. My n points and then the 3 in the middle that give me my 4 rectangles. So let me sort of, if I switch to our whiteboard again, if we go back to how about we're going to do this. Typically, we would say this is 0 to 1, and if we wanted 4 rectangles, we would do this. We would call this would be 1/4, 2/4, 3/4. And remember, your distance between these guys was delta x, which of course in this problem is 1 minus 0 over 4. Now, what we did in the textbooks, and this is going to be misleading now, is we gave these guys, we called this guy x sub 0, we called this guy x sub 1, this guy x sub 2, this guy x sub 3, and then this guy x sub 4. But we can't do it that way because the computer doesn't know x sub 0. It doesn't make sense to the computer. Octave can't make sense of that. So what we have to do on the computers, we have to renumber them. So what do I mean by renumbering them? Well, we'll call this guy x sub 1, this guy x sub 2, this guy x sub 3, this guy x sub 4, and this guy x sub 5. So this is why if you go back to Octave, that is why I am going from n to, I'm going to n plus 1, so I have to go up to the 5th guy. I start at 1 and I go to the 5th. And that's why I have this shift in the k minus 1. So the first guy, again, if you look at your notes from calculus, you'll see this formula. Only it would be written, you know. So notice what happens when k is 1. When k is 1, you get x sub 1 equals a. What happens when k is 2? Well, you get x sub 2 equals a plus delta x. And then when k is 3. So if you do each one separately, at least even in your head or write it out, you'll see it makes sense. So what does this thing do? What this does is this computes the partition is the fancy word. We called it. So this was x sub 1, x sub 2, all the way up to x sub n plus 1. So that's what it does. And then what we have to do is we need to calculate the heights. So how do we compute the heights of each rectangle? We don't want to do them all by hand, so we do the same thing. We say 4. Pick a letter. We ought to use K, so let's use a different letter. How about J? So for J equals 1 to n plus 1. We need to do the same thing. So now we have to evaluate F. So okay, so at this point, let me pause for a second because maybe this is not the most natural way to think about it. So technically we don't even have to do this. I mean, let's, okay, well maybe we will. So let's give these guys a name. So let's I can't use, I'm trying to think of the best way to do this so it's not confusing. So, okay, I got a better idea. Here's maybe a better way to think about it. So we have all our x values now. So why don't we compute the height of each rectangle, or compute the height at each input? That's a better way of saying it. So what I'm going to do is I am just going to, I'm going to use the, I'm trying to think of the best way to do this so that it's not so confusing. So what the nice thing about what Octave does is it literally, since I have all those x values, if I just put f and then I put parenthesis x, it's going to spit out f evaluated at each point of x. So let's watch what I mean by this, and hopefully you can make sense of it. So if I hit run, oh, I got to save it first. Forgot to save. So let me copy this file. And so paste it. So when I run this, watch what happens. Notice what happens when I square 0. I get 0. And then what happens when I square a quarter? I get a 16th. What happens when I square a half? When I square a half, I get a quarter. And so look at these numbers that it just listed. That is each of your x's squared. So if you took your inputs and squared them, there you go. And then all you want to do now is that computes the heights. And so since we know it works, we don't even have to compute the heights. What we can do is we can just compute the sum. So what is the sum? Well, the sum is, so our integral is approximately, what is it? Well, it's delta x. Remember, it's the width, so it's dx times the sum of the heights. Now, that means I just say sum f of x. That sums it. So this might be a little bit of a learning curve. Now, what I typed in is not correct yet because it's going to give us the wrong answer, and we're going to show you why in a second. But what I want you to see is when I hit this and go, I'm going to get a number. So I get 0.468, which that doesn't make much sense. If you guys do this integral by hand, you know what the answer is. The answer is 1/3, right? Integrate x squared from 0 to 1, you get 1/3. So what we're doing wrong here is we're not doing a left or right Riemann sum. We're calculating an extra piece. So what we need to do is we need to subtract off all right, so again, let's go back to, let's go back to our whiteboard. If I have this x squared creature, change color. So we're going to draw it twice. So if I want to do, remember with the Riemann sums, there's lots of options. Let's just look at the curve. It looks like this. So I could, if I do a right Riemann sum, that means that when I break this into 4 pieces, so this is 1, that means it looks like this. So if I do a right Riemann sum, I get these 4 rectangles that approximate it. So this is, of course, 1/4, 2/4, 3/4. So we call this is called the right Riemann sum. Now, if I draw a similar picture, only I use different rectangles, so if I try to mimic this picture best I can, it's a little ugly, but you get the point. So now if I use, so let's take pink and I break it up into 4 equal pieces again, but this time I'm going to use the left-hand side. So here I don't have a rectangle, I have this. So this is called a, whoa, that's a crooked one. So now I have these, this is really just 3 rectangles because the one is height 0. So we call this a left Riemann sum. So what I did, and the reason I got the incorrect answer earlier was because what I was doing is I was calculating the value, and I was doing, I wasn't doing these 4 rectangles or these, 4/3 rectangles. What I was doing is I wasn't doing that. And so if I go back to my screen, and hopefully you're seeing Octave, what I need to do is I need to subtract off. So for the left sum, so let's say a left sum, the left sum means we're going to not use the right endpoint. So that means before we calculate this sum, we need to subtract off the very last piece. So how do we subtract off the last piece? Well, that is f evaluated at x of n plus 1. So this is going to be very confusing the first time you do it. And then, of course, the right sum would be this thing, but we're going to subtract off the first piece, the first endpoint. So that would be subtract off x of 1. So it's going to take some time to learn this. And what happens is when we run it, we're going to get numbers, and these don't look very good either. But that's okay because we're only using 4 rectangles. And if you did it by hand, these are the numbers you would get. But what if I go up here and instead of doing 4, I do, say, 40 rectangles? Now that would take you a heck of a long time to do by hand. But when I do that, what I get is something that seems more realistic. My left sum, which we guess should be an underestimate because of the picture, I get 0.32. And with a right sum, I get 0.34. Okay, well, what about 400? If I do 400 now, well, now we're getting somewhere because look at these answers, 0.33, 0.33. I mean, again, we know the answer, the exact answer is 1/3. So we feel like we're doing something right. And why stop at 400? Why not go to 4,000? Would you want to compute 4,000 rectangle areas? I doubt it. And then you wouldn't want to add them all up. The computer has no problem doing it. It just does it. And now you see the left and the right. Look what's happening as we expect. They're converging. They're coming to the same number. So what I would do is I would study this example. And heck, why not go more? Let's do 40,000 rectangles. Now things are cooking, right? Does anybody have a question about this? comment?
Can you go back to the editor real quick, please?
Yeah, sure. What's up?
I was just looking because mine is not working.
Yours is not working. Make sure because if you have one little thing off, it's going to mess up. So one of the places you can make errors real easily is down at the bottom with the all those parentheses. You can also have an error is your F defined with F? Is it X periods caret 2?
Yeah, I think the arrow is at like white sum. It's like it's an arrow at this white sum for some reason.
Okay, I wonder why. So make sure you have the same amount of parentheses.
1, 2, 3. I believe I do.
Yeah, so the one nice thing, what's that?
It's left sum is equal to delta x times sum, right?
Well, not times sum, it's times this big quantity. So notice so work from the inside out. This is sort of like your order of operations nightmares when you're in like 6th grade. I'm taking the sum, that's adding all the F's together. But I don't want them all because I need to ignore the right endpoint. So I subtract it off. And then once I get that number, I'm multiplying it by dx. And then the same thing with the front, or excuse me, with the right sum. I take I add every F up, but I subtract off the front one because I don't want it, the very first one. That's why you have, so that's where that's coming from.
Oh, okay, I got it, I think.
Yeah. And like I said, when you're trying to get this to work, it's always good to start with small numbers so you can sort of work out any issues. Is it working now?
Yes, I think it is. Yeah.
Very good. Yeah. And like I said, then you can do even more sophisticated ones. You can learn how to use the midpoint rule. That's pretty simple too. You could just modify a little bit for that, and then Simpson's rule, and then trapezoid rule. You might remember those formulas. They're very easy to program that we talked about in Calc 2.
Yeah.
All right. Any other questions about this or any of the other homework problems?
How are we like submitting this? Are we like taking a picture or something?
Yeah. So that's a good question. Here's what I would like. It would be nice. I mean, if I'm not suggesting, I mean, I want you to be able to just do this. In an ideal world, it'd be nice if you can get it to display like a table. That's actually a little more difficult to do, but if you just want to, if you want to sort of, whether you just write down, maybe you make a table by hand. You say when n is this, here's what we get. When n is this, here's what we get. So what I mean by that is, if you, probably the easiest way to do it. And again, I'm not going to be real strict on it. I mean, I'm interested to see how you guys think it's good to share. But one way to do this would just be to make a table. You can say like n, and then you could say left, and then right. And then maybe you do like a couple values. Maybe you do like 10, 100, 1,000, and then you just list them by hand. You could type it into Excel if you want to use Excel, or if you want to use Word, or if you want to do it by paper and take a picture. That's fine too. However you best, whatever's easier for you, to be honest. And you could see I'm not being very descriptive on homework problems 2 and 3. It's just whatever you think you can do. That's all. All right. Now, for instance, for number 1, I mean, if you want to take a picture, that's fine. Or if you just want to submit your code's fine too. That's up to you.
Okay.
All right.
Okay.
Does that make sense?
Yep. Yeah.
Any other questions? All right. Well, listen, why don't you guys work on this stuff? And then you notice I put a project up. That's like an extension of number 3. So, see what you can work with that. And if you have any questions, let me know. We can meet and talk about it, or we can talk on it on Monday. But really, ultimately, the best way to learn this is for you to get your hands dirty, which means you go and try doing it on your own. And when you get stuck, you can ask questions, or you go to Google and say, how do I do blah in MATLAB? And you know what? If you start looking for Riemann sums in Octave or MATLAB, you're going to probably find very nice polished code that's already made. You can steal it. And I don't mean stealing in a bad way. That's what you do. You modify other people's code. And you're also going to find some really, really sophisticated stuff that's going to confuse you. But there's lots of different, I mean, there's lots of different ways of doing this stuff. You know, Abdullah, really, I mean, if I wanted to, I could say, I want you to write a code that the user plugs in f of x equals, and then it does everything for you. But that's a heck of a lot harder to write than what we're doing here. You know, kind of like, I mean, obviously you've seen Wolfram before. I mean, you think about how sophisticated Wolfram is. You literally just type it, integrate blah from blah to blah, and it knows what you mean, right? So, I mean, you could do super sophisticated stuff, but we just want to do simple computation right now. Remember, our ultimate goal is this is Math Neuro, and we want to get that picture, and which means we're going to have to use the MATLAB and Octave to solve a system of equations, and we have to build up to that. All right.
Okay.
Any other questions? So you guys are doing good. This is good. I mean, you're learning, which is even more important. So learning something. Good tools. And by the way, like I said, Abdul, if you stick with engineering and Zation, I know that's an option for you too. I mean, you will be using things like MATLAB and Octave all the time. So you might as well get used to it. And trust me, it's not hard. It makes your life easier. There's so many cool problems that you can easily solve and study once you know how to write simple things like for loops. I promise you, it might be annoying now. It might seem weird, and it might seem unuseful. It might seem more of like a pain than anything, but I promise you, once you learn even the basics, it'll be very, very helpful. In other classes too, when you take things like linear algebra and stuff like that, it'll be very useful. So. All right. Well, listen, I'll let you guys go because hearing me talk is not the way to learn all day. So hopefully you guys will put some work into this. And if you have questions, you'll let me know. Do we have any questions other than that? Good?
Nope.
All right. Well, thank you guys, and good luck, and stay safe. And I hope to talk to you soon. Be safe, guys. Take care.
Thank you.
Yep.